All right, so assuming you guys have that, go ahead and open that the non-O data set. And now the basic issue, right, with non-orthogonal designs or designs in which you have not equal sample sizes is that your estimates of your factors are not independent from each other. So for those of you who read Mark's article and the follow-up to it, the Kramer and Applebaum, the issue is pretty easily resolved just by running sequential tests. So doing these model comparisons that we were doing in regression, but doing them for analysis of variance. Now remember with orthogonal design, so when you have equal sample sizes, your factors are independent. So running sequential sums of squares wouldn't actually give you different information because your estimate of B eliminating A is the same as your estimate of B ignoring A. But in these designs, and you can see that this is actually non-orthogonal if we just fit your factors against each other. So in this design, you can see we have vastly unequal sample sizes. So factor B level A and factor, I should have really given these different names. It's going to be annoying. Anyway, AA here is, we only have very few numbers of subjects, and our largest is AB here. So you see it's definitely unequal. So not only within each factor, but across the factors distribution. So our estimates when we fit this model, and we can just go ahead and do it under Analyze and Fit Model like we normally would, our estimates of the two factors are not going to be independent of each other. So let's fit the full factorial and then just run it. And notice we didn't have to do anything different to run the analysis. But the point that's made in that paper and has been made subsequently is that these estimates are not independent. So for factor A and factor B, these estimates are not orthogonal like they are when you have equal sample sizes. And so when you're looking at these, and actually this is probably not the best example of a data set because once you have one of these factors significant here, that's essentially telling you factor A eliminating B is now statistically significant. We already are in this set of sort of models where we know we have to use A. So let me actually pull up from Mark's article this little table, a handy one to have. So for those of you who read it, and this is what Mark drew on the board on Thursday. So these are really 7 patterns of results you can get in a non-orthogonal analysis of variance. And they basically point to different factors that you should have in your full model. Right? So assuming at the offset here that you have both an A and B statistically significant effect, so A eliminating B and B eliminating A, which is essentially what these effect tests are giving you. Remember in regression, your coefficients here were always partial regression coefficients. It was the effect of that factor or that coefficient excluding everything else. The same thing is true here. It's just we don't really talk about them as partial regression coefficients in analysis of variance when they're orthogonal because there's no correlation there. This effect is the same whether you have B in the model or not. But in non-orthogonal designs, when we have unequal sample sizes, this effect, so factor A, eliminating B, which is what's printed here, that'll be different than just the effect of factor A without B, right, the ignoring test. So these patterns that we have over here really point to different types of models you have to have in order to fully explain what's going on in nature. But if you have, notice, either of the A eliminating B or B eliminating A effects statistically significant, it really doesn't matter if A ignoring B or B ignoring A are significant. That's just what the X's mean here. It's just an irrelevant test. Right? If you have an effect of A eliminating B, you know A is going to be important because it's important even when you eliminate all the variance that B accounts for. Same thing with B eliminating A. If that's statistically significant, you know you have to have B in your model because it's still having an effect even once you remove A. But it gets to these strange situations over here that sort of complicate things for these non-orthogonal designs. When an A eliminating B or B eliminating A test is not statistically significant, but either A or B alone are statistically significant. So my point here is that if these tests come up statistically significant here, you're pretty much assured that that's an important factor because these are essentially the test of A eliminating B and B eliminating A. Now, assuming, if I just made this data set a little different, that neither of these came up statistically significant, you might decide, oh, nothing's happening in my data, right? I've just decided that nothing had an effect. But what you would want to do is check on these A ignoring B and B ignoring A effects, right? So you have to check these final 2 rows. Because you could be in a situation like number 5 or 6 or 7 where A has an effect if you don't consider B, and B has an effect when you don't consider A. But combined, they soak up so much overlapping variance that neither comes up statistically significant. And so you remember in regression, to get those tests, those ignoring tests, we simply go into estimates and request the sequential tests. And what you'll get at the bottom are those type 1 sums of squares where the factors are entered in sequentially. So this effect here, so factor A, now is the effect of factor A ignoring B. So if B was not even included in the model. And actually it's being fit in that sense, right? B isn't being considered until you get to the second step. So that would actually give us this A ignoring B test. To get B ignoring A, remember what we did in regression is we just refit the model. And a quick way to do this is just go to script, relaunch analysis, or you could just go to fit model. We're going to do data again as what we're predicting, but now we're going to put B in before A. And when we do it this way, we actually have to construct the factorial ourselves because there's no macro to switch the orders. So you just select both and hit cross. So again, we have the full factorial, but notice now that factor B is the first factor that's going to be considered. So when we do the sequential test, that's what it's going to give us, the B ignoring A test. So if we run this, we can again go and request the sequential sums of squares. And we can now have that test of B ignoring A. And so what we find in this, and this is what we would assume to find because we had this statistically significant result up here for the effect of factor A, that factor A is really the thing that's important to us here. And you'll notice that even when we already have removed B, factor A is statistically significant, because this is essentially the same test as when we have it up here in the effects test section. Because again, just like in regression, these are the tests as if everything else has been taken out of the model. So really the upshot for our point of view is you can run non-orthogonal designs exactly the same in JMP. It does the computations correctly using a general linear model. It doesn't have the same problems that the original analysis of variance had, at least in this fitting. But notice that you can get a situation where neither of your factors come up statistically significant, but there's still going to be something happening in your data. So at least my advice would be if you have very unequal sample sizes and neither of these come up statistically significant, the thing to do is go through those sequential tests. Make sure that you don't have something hiding in your data that is being essentially covered up by the fact that you're doing eliminating tests up here. But I mean, if both of these come up statistically significant, you could be reasonably assured you have that effect. Those are your eliminating tests. And as with all these things, if you have your interaction statistically significant, you shouldn't even be considering dropping terms because your interaction is statistically significant. You really need everything in the model. And I think Mark mentioned this too in social sciences. Typically, we don't remove lower order terms and keep the interactions. There are fields in which that happens. It seems a little bit strange to me. I can't really grasp what model they're really constructing there, but for us at least, if you have the interaction term, you're never going to eliminate the A factor or the B factor. You just keep the whole model swarm. Okay, so for non-orthogonal analysis of variances, you can do these things just as you have done before, but again, just be comfortable with the idea that if you don't get a statistically significant result here, that's not the entire story when you have unequal sample sizes, because there's still going to be something that's happening where these factors share so much of the variance, or they share so much of their explanatory power, that they cover up each other's effects. It's like, remember with outliers, if you have a couple extreme outliers, they can hide each other because they actually affect the model such that one covers the other. It's actually not at all the same thing here, but what you're still getting is one factor's effect can cover the other. Just like in regression, you can overfit, multicollinearity, things account for the same variance, and so neither will look statistically significant, and that's what can happen here with unequal sample sizes. Okay, is everyone fairly comfortable with that? I mean, the sequential sums of squares we've done before. Really the thing to, I think, take away from this is, read the article, check out the table. It's really these 5, 6, and 7 situations that cause a problem for us. Of course, situation 4, we can make a decision there pretty easily. 3, 2, and 1, also we can make the decisions, but these are the indeterminate situations where really, the best thing to do, well, the worst thing to do is throwing away data. Don't throw away data. The best thing to do is collect more data and even out the design if you can. That'll give your model the ability to actually distinguish where the effects are coming from. But again, these situations can occur, especially when you have really unequal sample sizes, and your effects are really not terribly large. And if you have a very large effect of either A or B, it's probably not going to be so sufficiently watered down by the other factor that you'll miss it. But if you're in a situation with small sample sizes and unequal sample sizes, this can definitely happen. Okay, so that's all I really have for the non-orthogonal stuff. What I want to do now, though, is start with just an example data set, this chapter 27, number 2, to look at a situation where instead of running totally between designs, so where each person only contributes one data point and all the manipulations are between subject, a situation where it's either more efficient or necessary to run designs where we have people give us multiple responses. So this is the typical repeated measures or within subject manipulation type experiment. And so in these designs, and in this one in particular, what you do is you have subjects occur multiple times in your data set, right? And they're giving you multiple responses under different conditions. And the original sort of origin of all these was in longitudinal designs. We take kids or critters or whatever and measure them across their lifespan and really plot trajectories, see how they advance or how they grow. But it turns out that the same sort of statistical models can be used to extract the variance unique to the organism, so the individual unit that you're replicating over. Take that variance out so that your mean square error, or your error of the model, is uncontaminated by that variability. So in this situation, what we have is, it looks like 6 judges, and we've given them 4 different wines. But remember last time we had this example, we gave everybody a different wine. In this case, the people are actually getting all 4 of the wines, so all 4 of the different conditions that they're in. And they're giving ratings. This isn't my data set, this is the book, so I have no idea what this scale is. It looks like 0 to 30 or 20 to 30, I don't know. Who knows what it could be, 10 to 30. But they're giving ratings of these wines, right? And what we're going to be able to do with these random effects models, or these within subject sort of analyses, is remove the effect of judge from this situation. We want to know what the effect is of wine, but of course we're contaminating our ratings, or we're confounding them completely with the judge. Right? So judge 1 may be a wine critic, judge 2 can just be a, I don't know, I was going to say a dumbass, but I don't know, non-wine enthusiast. Wine taster 4 could be, I don't know, just uninterested in our experiment or something. I mean, everybody has their own unique things that are going to come to their own, data points, or it's going to get filtered in there. So what we want to do is say, okay, let's imagine that, judge wasn't really a element in our design. Let's remove that variability and look at the uncontaminated effect of wine. So to do this, we're going to fit it just like we did with that block model, right? But we're going to have to do something special with this judge column. We have to tell the model essentially that these judges are random selections from some greater pool. So let's first start by putting rating in our Y. And what we're going to do is, like we did before, not fit an interaction because we don't have the degrees of freedom for that, nor do we think conceptually that's interesting, or maybe we do. What we're trying to find, right, is overall main effects of wine. If every person has a different conception of the wine and it's totally varied for each person, then we never really can talk about an effect of wine, right? So think about that with most within subject studies. There were complete interactions with every subject so that everybody was different, then we can never say anything about the factors. That would be totally contextualized within the person. So we're not fitting an interaction, both because we don't have the degrees of freedom, but also because we don't think about it that way. So we're just going to put these 2 factors in, the model effects. Now if we ran it like this, it's going to do that randomized complete block design type, or it's going to think that's what we're doing here. But remember, judge is actually not a fixed factor. If we were to rerun this study, we wouldn't have the exact same judges, right? These aren't fixed parameters in the world. We're not going to get judge 1 through 6 here. They're not people that we would re-sample, presumably. So what we're doing with the judge sort of factor here is we're going to consider a random effect. And Mark only talked about this briefly, but to do that, just go to Attributes and select Random. And what this converts this model into is one of these random effects models, or mixed models. Because what we're doing is fitting the fixed factor, wine, as a, let me see if I can pull this up here. We're fitting the fixed factor wine as actual means or treatment effects. We're going to say what's the effect of having wine 1, 2, 3, or 4. But the effect of judge is actually considered a random variable. Because each person, presumably, comes from some distribution of, let's say, I don't know, it's a kind of combination of all factors, how much they like wine, how interested they are in the study, how hungover they are, because maybe that's going to affect their ratings too. But they come from some distribution with some mean, right? And so some people are going to give higher ratings on average than others, right? So all the factors that contribute to your idiosyncratic score or something unique to you is going to filter into all your data. So really what we're assuming with this model is that we have, for each individual, some overall mean, right? That unique personal effect, right? So a place that you sit where the treatments are going to add or subtract to. Then we have for each treatment, we have some factor level. So wine 4 versus wine 2 or wine 2 versus 1, how much of an effect that makes. And then we just have just general error here. So sampling error within a person within a wine. So remember, if I were to take the same person even and give them the same wine, even though we've accounted for that person difference up here, that same person has variability in their ratings over time. There's still error there. We wouldn't be able to fit that perfectly even if we did take the person back. So the model we're fitting here, again, has no interaction. We're fitting, instead of constant effects for each person, we're assuming that they come from some distribution, right? And we're going to be able to partition or take components of variance and say how much variance is accounted for just by that variability in people, and remove that from the denominator or from the mean square error. So to do that in JMP, we just tell it it's random, right? And notice one thing changed over here. Well, the emphasis and personality is the same, but method we now have a selection. So the recommended method, and this is recommended in SAS and JMP, is Remmel. This is the same as LMER in R if you guys use R. It's just linear mixed models, reduced maximum likelihood estimation. You can do EMS. This is a different or the older way of doing these kind of mixed models. It's listed as traditional. If you look in the manual, JMP actually says they only keep it in there just for pedagogical reasons, or if people have to match their results to older analyses. So if you have to do, this is the method of moments, you can do this, but just keep it on Remmel if you don't have any reason not to. This is going to be the best way to do it. And everything else here, you could just leave the same. And this is going to perform for us this random effects model with an actual fixed factor. So we have a fixed factor of wine and a random effects of person. And you're going to notice we have one new section here, this Remmel variance component estimates. And we're going to come back to this. But notice here under judge, we have this section called variance component. So this is the variance it is determined is accountable or contributing from the judges. So 8.4 on whatever scale our metric was in. That's the variance that is just contributed from differences across people. And then in our fixed effect test, we actually have our standard effect that we're used to seeing, right? So what the effect of wine is. And notice that everything is as we would expect. There's 4 levels. We have 3 degrees of freedom. It gives us the denominator degrees of freedom for the error term. And it gives us our F ratio and our p-value. And really everything in this is the same. If we want to, we can go and run our 2 keys comparison, looking at all the differences in wines. We can see that 3 and 4 are essentially the same, but differ from 2 and 1. So all of that's the same. It's going to use the appropriate error term, the one that's uncontaminated by subject. And if we're really interested, we can look at the differences in judges. So we can see that certain judges are a little more favorable or found the wine to be better overall. Some judges were low. But notice that the variability here across these subjects, that's what that variance component is. That's the variance attributable to differences amongst people that we don't really care about, right? We don't care that people are differing among themselves in their base point. We just care that there's differences off that base point for each wine. So if you think about what the model's really doing, and I'm just going to show you something this isn't conceptually, or not conceptually, isn't, I don't know why I did that. Let me back up here. This isn't an analytic strategy. This is just a trick that we saw before, right, to get those plots for us. So I'm going to fit the interaction term in there, just so I could show you that for each person. Why are you up there? That's so strange. So here's our plot across all individuals. You notice that what the model's really hoping to find is that there's differences amongst judges. That's that plot that we had before, the judge difference. But really that everyone's really behaving the same way, that there's not that judge by wine interaction. That even though judge 6 is extremely critical, he or she still finds wine 3 to be, so much more than wine 1. So it's taking that really idea that everyone's really behaving the same way, it's just that they started somewhere different. And that difference is attributable to, all of the unique characteristics of that person. So this is really all you have to do for this analysis. If you have random effects, the really most important thing I can point out right now is your data set has to be laid out this way. This is called stacked. So we're not splitting columns. So every judge, if you have 4 observations for judge 1, judge 1 will take up 4 rows, right? SPSS for repeated measures experiments like split files. So each judge takes up 1 place and you have 4 columns, right? So we'll talk about that in a second. But for JMP, you have to have it like this, right? Because what it's really considering this is a blocked type model. So your subjects or your judges are just random blocks. You're observing them over multiple times, and you can estimate for them the effect of a fixed effect. Yeah, Patrick.
What would you do if one of your judges or subjects was, or a group of them, just were fundamentally different?
Yeah, so actually conceptually have different characteristics.
What would be the next step?
I mean, it really depends. If you think there's something actually qualitatively different about them that you can measure beforehand, the best thing to do would be measure them, do the analysis, and have as another factor what group they fall into. And then you just fit it as just, you can have an interaction with your treatment effect. So you can see, does your effect of, let's say we have, in this model, people who are experienced with wine or not experienced, or professional versus not professional wine tasters. So I would just make a new column here, which is, type. And then for, let's say, 1 through 3 are professional wine tasters. So I would just mark, wow, I don't know what that was about. There we go. And then just do B here for the other wine tasters. Okay, over that. Man, I am not good at doing that on the fly. A. So you have, right, basically something that qualifies or denotes whether they're this professional or not. And then the model you would be fitting, I assume, would be you'd want to first put in judge. That's just your random effect, baseline effect there. And then what we can do is fit the wine by type interaction, so fit the full factorial. And then what we're really making statements about here is whether there's not only an effect of the wine, but whether there's a type difference. Do those 2 groups have different averages? And the interaction, which is probably most interesting, is there a difference in their sort of profile of effect? Right, so if this was statistically significant, it might be that people, well, we could just see actually with my random nonsense coding here. So it maybe might be that the wine tasters, professional ones, liked 2 different wines better than the non-professionals, or they just crossed over, or whatever their situation is. But yeah, I mean, it's as simple as that. You just put it as another factor, and then you just see what effect it has. Now, I mean, if this was a difference that you could predict beforehand, it's a little stronger sort of experimentally. But it doesn't matter that it's not. I mean, this is still, you just have to understand that it's one of these post hoc sort of, splits. It's like doing median splits on your file and saying, top versus bottom. It's data driven, so it does have the chance of sort of capitalizing on what already occurred in your unique data set. But, it doesn't make it invalid. It's still an interesting sort of question in most cases. Yeah. Okay, so any questions about how I fit really the model and all these things? What we're going to do is poke through this Remmel variance component estimate section to sort of get at what these things mean a little bit. But at least as far as the JMP side, we're all fairly comfortable with that. So let's do something here. Let's actually build a data set that has all the components that we're using the model to re-extract, right? Because that's really what's happening, right? Nature gives you data that comes from some process, and then we're using statistical methods to get back at what we think is true about nature. So let's just play that part of nature and actually come up with our data first, and we can see how the components get sort of extracted by the model or where they end up. And I think this is at least helpful, especially with these random effects models, because we can see what we're talking about when we say a variance component due to subjects. So let's imagine a situation where what we're trying to do is see the effect of, let's say, some drug over time for people's IQ, right? So we're going to have a bunch of subjects. So let's actually just make a column called subject number. All right. Let's make another column. I'm going to call this subject base IQ, which, for our purposes, is just going to be whatever IQ they actually have coming into our study. Let's imagine, though, that this is something we didn't measure. This is just something that we're going to, as sort of creating the data set, we know. You'll see where that comes in. And let's imagine we have these IQ measurements. So IQ 1, so the first time we measure their IQ. I'm going to make another column, IQ2. And I'm just going to do this all the way until I get to IQ4. That one's weird. I'll fix that. Obsessive. Okay. And so what we're going to do with this is populate this data set to have, for each subject, right, 4 scores. And it's going to be these 4 scores that we're going to end up getting as researchers from this data set. This base IQ is just going to be this component of them that is unique to that person. And you'll see how we're going to use that. So we need to give a bunch of unique subject numbers. The easiest way is we're just going to have JMP produce for us a bunch of numbers from a uniform distribution. So it's actually going to formula for that column. And what I want you to do is scroll down to random and just select random uniform. Now what this function will do, before you actually run it, the thing you have to do is just click somewhere on the side here to add some rows. So I just double clicked apparently on row 16. Just get some blank data points in there. Now if I hit apply, what random uniform does is just picks a uniform number from 0 to 1, right? But if I wanted subject numbers that weren't like tiny fractions, we can easily, if you notice, just double click on this, take the whole thing and multiply that by, let's say, 10,000. And notice now that we have a little bit better for our subject numbers. I still think that's kind of ugly. So I'm going to double click on this whole section. And I'm actually going to type round, and then just put an open parenthesis, and then close the parenthesis at the end. So it should look like this once you're done. Oh, and we have to tell how many digits to round. So, sorry, you have to do round, whatever you're trying to round, and then how many digits you want. And I'm going to do 0. And this is totally unnecessary. It's just, you know, makes it look nicer. There we go. So now we have subject numbers. We probably won't have any repeats. But, you know, let's hope not. If you don't have 16 subjects, go ahead and click down to 16. If you have more than that, that's fine. Our numbers aren't going to match, obviously, because we're going to do a lot of random number generation here. But you want to have at least about 16 people here so we can actually find some effects. Okay, so let's start with subject base IQ. So what we're going to do here is just for every subject, we're going to determine some base IQ for them. For most IQ tests, they're centered at 100. Standard deviation of 15. So what we're going to do is for this column, go back to that random. And we know IQ is generally normally distributed, so let's just do random normal. Now notice what random normal will do, if we just hit apply, it's just going to give us a random selection from a standard normal or a unit normal distribution, so a mean of 0, standard deviation of 1. We can rescale that however we want by just doing a simple trick. Take the mean, 100, plus whatever we want the standard deviation to be, 15 times that. So what this will do, if you type this in here, will give us, instead of a unit normal distribution for that column, it'll give us a IQ distribution, 100 with a standard deviation of 15. So go ahead and hit apply. Great, so now every person, right, has a starting IQ. This is just something idiosyncratic to them. It has nothing to do with other people, just everything to do with them. And if you wanted to be nice about it, you can round this off too. Actually, I'm not even going to do that because it's unnecessary. But of course, we could probably never measure people's IQ to that precision, so that's fine. Okay, so now we have to think about what effect we want. So across time, let's say we're doing, I don't know, the effect of, what's the common one, blue-green algae, or cyanobacteria, let's say in pill form. Something that maybe will or will not have some effect, but we're testing it. But let's say it actually will increase IQ over time. That it takes whatever the person's starting IQ is and increases it by the 4th week, let's say these are weeks, by up to like 6 points. But it takes some time to get there. So let's actually start with the last person, or the last observation, go into the formula there. And notice that what our model is really going to say for any one person is that the effect of that observation point, or the score for any particular cell, is just that person's original base IQ, right, plus, we can do this, and then what we're going to do is some random distribution around whatever we think the true effect is. So we said 6-point increase, I think it was, by the 4th week. So let's actually go down to our random section here, do another random normal. Let's assume that the distribution around that point is normal. And remember, this is going to give us a standard normal. We want to actually give it some, you know, the actual amount we want. So 6 plus, and then we have to just choose arbitrarily some standard deviation. Let's say it's 2. I don't know, that sounds about right. So a little bit of variability in there, but not so much. And notice it'll do the parentheses and all that for you. So if we hit apply, so now this is everybody's score after the first week, but a component of that score, of course, is their baseline, right? So where they started. But the rest of the score is some effect that's consistent across people. It's independent of their original starting score, 6 points, and then plus some extra random noise that accounts for day-to-day variability, something not due to them as a person, but due to just that particular observation. Okay, now for just simplicity, if you double-click on the outside box, you can take that whole function. I'm just going to copy it, because we're going to do this for the other ones, and we don't have to recreate our structure. So again, just get that outer box. If you just double-click on the very outside, you can copy that whole function. Okay, so we're going to go into IQ3 now. Go to Formula. Easiest way, just double-click in the formula box and paste that whole function. But of course, at IQ after 3 weeks, we don't want them to already have achieved 6 on average. Let's put them maybe 4 points higher. So still a decent increase. And hit apply. And so now the average across all people are from the population, right? Because that's essentially what we're doing here is the population distribution that creates this is 4 points higher. So there's still some effect here, less so than the 4th week, where we're still increasing. So let's go to 2, and you probably can guess what we're going to do here. Same thing. Let's take the score down. So we had 4 for the 3rd week. Let's say 3, maybe. And I'm going to do 2 for the 1st week, so it slowly goes up faster, let's say. The actual function there isn't terribly important, but I don't know. I'm in charge, so I get to decide. And let's do the 1st, and let's put it at 2. Yeah. So 2-point increase, but it's just 1 standard deviation. And these are actually pretty massive effects, right? So we, within the 1st week, have increased their IQ, what is this? What's 2 or 15? Whatever that is. Some amount. A lot. That's 2-point increase in IQ. If you can get that after a week, I would take that drug. Okay. So let's just, again, not forget what we're doing here, right? So these are 16 subjects. We've observed them over 4 time points, right? And their IQ at each time point is a component of what the real effect is of being in the condition, right, or of being in that time frame. And also a component of it is their base IQ. Now, just for fun, before we actually run the analysis on this, let's check out the distribution of base IQ here. All right, so this is just our base IQ distribution. I'm going to go under here and actually request more moments. So under display options, more moments. And notice the variance of this is 268. So the variance of my base IQ scores here for these people is 268. Remember, we set it to be actually 225. So standard deviation of 15, but we just took a sample of 16 people, so that's not too surprising, right? The variance of our sample is going to be different than the population variance. But just remember that 268 is the variance of these people's base scores, the component of their score that's just the base, right? Their base IQ. Okay, so I told you before, this is how SPSS and a lot of other programs would love to have your data for repeated measures. It's not how JMP likes it. JMP likes what's called the stack. To get from here to a stack, you can do a couple things. The quickest, just go to tables. Not surprisingly, go to stack. And it's going to ask us for a bunch of things, but basically all you have to give it are the rows that are accounting for your repeated observations. And what it's going to do is the other rows will just be replicated across the stack. So you'll see what happens here. Take your IQ 1 through 4, give them to it as the stack column. Everything else you can leave the same, but I like to change these things because it just makes more sense. The stacked data column, this is actually where your data points are going to be, and it's asking for what you want the label to be. I'm going to put this as IQ, because that's actually what the data are here. They're IQ scores. And then the source label, this is asking you what you want it to name the column that identifies these different IQ things. I would put this as time, right? Because time is really what we're spanning across over 4 different weeks. It could also be weeks, whatever you want. Everything else you can just keep the same. Go ahead and hit OK. And notice what it did here. So it took the columns we didn't put in under stack, and just replicated them across the stacked columns. So 1, 2, 3, 4 here. And it just copied over the IQ. Now notice this base IQ, of course, is the same for the subject over all times, right? But the IQ scores, just like we had here, are built out of essentially that base IQ plus some actual effect and some noise. Now the reason we didn't actually design the data set this way, doing the stack, is actually doing this. So having the same random score spanning 4 rows is tricky. It's a lot easier to just have every row in your data set take on a formula. If you do it the other way, you have to do a lot of matching things that is just not worth it. So if you're faking your data, start it this way, and then go ahead and stack it. No, I'm totally kidding. Don't fake your data. Really bad. Okay, so now we have this, right? Your data set's set up almost for doing our random effects model here. The only thing we have to do, though, is tell JMP that subject number is not continuous, right? It is a continuous number. It has numbers, right? But they don't mean anything continuous, right? The subject 3724 is not less than or greater than 3448, right? It's just a nominal category. It just identifies the person. So make sure you mark that as nominal, otherwise it's going to think you're doing something very, very different when you run that analysis. Okay, so let's go and actually fit the model. Remember how to do this. We're going to take IQ as the thing we're trying to predict. Subject number is going to be our random effect, so just put it in there and mark it as random. And then time is our only fixed effect in this case, right? We want to just see what the effect is over the week span. Everything else we can keep the same. Remmel is what we have selected. That's perfect. Go ahead and hit run. Let's close the model thing here. Now notice, surprisingly, under subject number, right, which is our random effect, this is the component that's due to just the person, the variance component here, 268. That should look very familiar to you guys, right? So that's the component it's extracted from, right, the previous data set. So if we go back over here and under the distribution for the base IQ, and then we request more moments to get the variance, 268.308. Right, so that component was just something due to the person. It had nothing to do with our effect. Right, remember that was just something added on to the IQ over time. Nothing to do with our effect. And similarly over here, that component has been extracted, right? That component of the overall variance is extracted and not contaminating our estimates of time, whether time actually has an effect. That's all a variance component model is doing. It's just pulling out these variances. Because remember, we didn't specify fixed levels for these people. We just specified a distribution with some variance, right? It's contributing error over some, distribution of people. That's all a random effects model is doing. It's just trying to recover this variance component so it can take it out of your overall denominator. Now notice this fixed effect. We can actually expand the details and look at our effective time. It doesn't look like anything when we have it scaled like that, so let's actually stretch it up. But if we look at the least squares means, we got kind of cruddy luck here with our sampling. Notice that we had originally set that last term to have a mean 6 higher, but we did not get a mean 6 higher with 16 people. So too bad for us. But we still were able to show an effect, so maybe we would, I don't know, this is the sad thing about making your own data, is you get to see firsthand how easy it is to not get the effect that was actually true in the population with small sample sizes. And you get to see how you would distort your own facts if this was what data you got, right? You would probably end up saying, look, the first step is the biggest, helps people out, but then, the effect of the drug is to not help you anymore. And we make some big claim that taking it after 4 weeks is not helpful, when really the effect we had for our subjects, right, was to be increasing in terms of its effect. Or not an increase, no, it was 1, 2, 3, 6.
Wouldn't you be saying,
two,
since IQ 1
three,
is supposed to be an increase of 2, it doesn't increase the first week, and then increases a lot in the second week?
Yeah. Well, what we put in here, right, was that the last week got the biggest increase.
Right.
Yeah. And then this one was 4. Yeah, what was the first week increase? It was just 2, right?
2.
Oh.
But you're getting
So
0 out
2,
there.
3. Yeah, really are.
0 is like.
Well, okay.
No effect over. Anyway, point is not super, but again, it drives home the fact that, small sample sizes, low power, you can sometimes distort your own results. Anyway, the point in showing you all this was really this piece, right? So noticing that what we've been able to do is remove that component. And notice that if we were to run this again, and this is not really kosher, of course, because we don't have independence amongst our individuals, right? So if we just ran it like this, didn't tell JMP that we had subjects as blocks. Right now we have 4 times as many subjects of things that are independent, but we've also contaminated the hell out of our variance with subject effects. And so notice that even with 4 times as many subjects it thinks, right, we have just diluted the hell out of this thing. Basically the effect is still the same, right? So the effective time is the same number of sums of squares that can account for, but our denominator here is completely contaminated with the between subject differences in IQ, which are way larger, of course, than the effect of time here. So a 6-point increase in time was our biggest effect versus the first point, or 4. And then the effect of IQ, I mean, just look at how huge these differences are amongst people. So contaminating that with between subject differences is just washing out this effect. The F ratio is tiny. But again, don't run this type of analysis. You've now basically 4 out of your 60. No, wait, I'm trying to think of proportion. Whatever. 1 in 4 of your people are not independent of each other, so that's not good. Okay, so random effects models, fairly simple. You can have multiple, random components. Your effect doesn't have to be something like subject, so you can have random effects models where your actual manipulation is random. So if you do a study in which you have, let's say, different times between, let's say, observations of something, or you have, I'm trying to think of what cognitive experiments would be, masking, where you have masking that's just chosen at random. So how long before something gets masked? That's a random effect. If you just let the computer decide, it has some distribution, and it can predict and remove that variance for you. And you can also make statements about random effects. It doesn't have to just be something you're removing. It could actually be something you're testing. But the model telling it that it's something that has a distribution is important because, right, you're not expecting over replications of the study to have the exact same observations, right? So if even within a subject you have lots of different masking times, the next subject is not going to get the exact same times. So JMP won't be looking for, 232 milliseconds mask for subject 2, even though subject 1 had it. So you can have, actual effects that you're interested in analyzed using variance components. Okay, that's actually all I had for today. Any questions about this stuff? We're going to talk about random effects more. I know Mark still has another lecture on it, and we'll get into nested models, which have some relationship because a lot of sort of the things overlap that we do with these different sort of model constructions. Nesting is also fairly simple to do in JMP. It's one of these things that just makes sure the interpretation's right. But yeah, that's all I have for now. What is it? Nothing tomorrow night. Remember, Wednesday was canceled. Thursday is going to be more random effects and multi-factor studies. And then I think next week we get into some logistic regression, and then we come back to nesting and some other repeated measures types of analyses. So yeah, if you guys have any questions, I'm done for today. Stick around if you have questions individually. But otherwise, see you Thursday. Actually, I won't see you Thursday. I'm going to be in Dallas. So see you next Tuesday.